Greetings, space enthusiast. You're now tuned into Space Forward.
Get ready to embark on an interstellar expedition
with forward-thinking space visionaries to explore the latest intriguing ideas
that are making our space future a reality.
I was taking almost like an indigenous view, going to the moon, living off the moon, building a technology on the moon, from the moon, rather than actually transporting a terrestrial technology with a vast infrastructure behind it. So I was looking at it from the point of view, I want to create a self-replicating machine on the moon. How can I get that out of the moon?
We're your host, Hussein Bukhari
and Kelly Kowalski. Get ready to blast off with Alex Ellery as we discuss the practicalities of extraterrestrial self-replicating robots as a means to shape a sustainable industrial lunar ecology.
The concept of sustainability is understood by everybody except space engineers. If we can imagine ourselves in the future, let's say we have to start building towns and things like that where people live and work on the moon, they are going to need water. What NASA wants to do is they want to take that very scarce and valuable water and they want to burn it as propellant. And if we burned it all, then they're not going to have that resource. What I think we should be doing with the water, we should be husbanding it. We should be taking care of it for future generations because they're going to need it for other processes. And if we're burning it, I think that's a terrible thing to do. And I think we're bringing all our bad habits with us by doing this.
So let's speak with Alex Ellery. He's an aerospace engineer and professor at Carleton University in Ottawa, Canada.
Yeah, I really enjoyed this conversation, in part because here at Space Forward, I joke with you and producer Matthias Franzel all the time about renaming this podcast as the Von Neumann podcast, because let's face it, you guys are obsessed with self-replicating robots.
Well, I mean, yeah, me and Matthias love our Von Neumann probes. Yeah.
We love our Von Neumann probes.
We love our probes.
And for those who might not be familiar with John Von Neumann, he was a brilliant, before his time, mathematician, computer scientist, and physicist who not only contributed to the fields of game theory and quantum mechanics, but also the concept of creating a universal constructor, essentially a machine that can make copies of itself. And as we find out from Ellery, well, self-replicating robots might be one way to settle the moon sustainably.
Well, yes. So Ellery calls this the industrial lunar ecology. It's essentially a way to extract and recycle resources within a closed environment like the moon. And as Ellery explains it, some of his thinking comes from the work of Dr. Adrian Boyer, who started the RepRap project, which stands for Replicating Rapid Prototyper. Try saying that 1,000 times, Kelly.
Replicating
rapid prototyper.
Wait. Replicating rapid prototyper. I did it.
Replicating rapid prototyper.
RepRap.
Essentially, it's a self-replicating 3D printer.
And you know what's crazy? Only a year ago, I was teasing you guys about Von Neumann probes, yet here we are in 2023. The company Relativity Space launched the first 3D printed rocket back in March. There's all this buzz about ChatGPT, the benefits and consequences of machine learning and artificial intelligence. And of course, there's the Artemis program. We're going back to the moon and we're going to land the first woman and the first person of color on the lunar surface.
Well, let's launch it with Professor Alex Ellery and find out why he stopped believing in extraterrestrials and started believing in self-replicating robots.
Alex Ellery, welcome to Space Forward.
Thank you very much. Thank you for having me. I'm delighted to be here.
Well, let's just start off, if you could tell us a little bit about your background and what sparked your interest in self-replicating technologies.
Sure. Well, my name is Alex Ellery. I'm a professor at Carleton University in Canada. My background is I originally started out as a physicist and then studied astronomy for a master's at the University of Sussex in the UK. And there I met John Barrow, who was one of my professors. And I'd always been interested in the question of extraterrestrial intelligence, having been weaned by Carl Sagan on his Royal Institution Christmas lectures and then later his Cosmos TV show. So I'd always been an arch believer in extraterrestrial intelligence, was interested in the SETI program. John Barrow was one of the few people actually at my institution, in the astronomy department, who actually had an interest in any of this. And he introduced me to his book, the Anthropic Cosmological Principle, wherein a chapter was written by his co-author Frank Tipler. And in this chapter, he introduced an argument which suggested that extraterrestrials do not exist, because if they did exist, they would have built self-replicating probes which could colonize the galaxy in fairly short order, astronomically speaking. And we should see signs of some evidence of them. I found this argument to be quite an epiphany, because it converted me essentially from a believer into a skeptic about extraterrestrial intelligence. But it also did something else. It basically made me almost obsessed with the idea of self-replicating machines. So when I finished at Sussex, I then went on to do a PhD in engineering rather than continuing in astronomy, specifically in space robotics. It was not possible to do a PhD in self-replicating machines at that time. Well, indeed, I'm not sure it is now. And for many years, as an academic, I started working on space manipulators and planetary rovers and planetary drills and so on. When I came to Canada, I was originally at Surrey Space Centre, and then came to Canada and continued in much the same vein. And then a few years ago, several things happened which coincided. One was that I started getting more involved in situ resource utilization on the moon specifically. The RepRap 3D printer came on the market, and I knew the person who had actually built it, Adrian Bowyer. I also was made full professor, so I felt I could start to do things. I felt I was freer to follow my own instincts, my own nose, as it were, rather than just simply going for money and things like that. So all these elements came together. So I started looking at self-replicating machines, not just as a concept, but from a pragmatic point of view, and in particular as a means to essentially industrialize the moon.
You mentioned the book, The Anthropic Cosmological Principle, right? Could you explain a little bit about how the authors arrived at their reasoning as to why we have not found ETIs or extraterrestrial intelligence?
Right, yes. The assumption has been that people like Carl Sagan and Jill Tarter and so on have always made the assumption that applied the Copernican principle, which is basically there's nothing special about us, so therefore there should be intelligent life elsewhere, given that they're bound to be other planets where have similar conditions to Earth, or close to similar conditions to Earth. And so if the process of the development of life and intelligent life is a kind of like a physico-chemical one, there should be other examples of intelligent life in the galaxy or elsewhere. Tipler's argument was that he takes it the other way around. He said there's no actually evidence of intelligent life elsewhere, and why might this be? And his argument was that any intelligent technological species will develop self-replication technology because of the sheer power that it affords. If the ETI develops self-replication technology, they will build self-replicating probes, or von Neumann probes is another term for them. It's an economic advantage. For a very, very low capital cost of sending one machine out, you can colonize the entire galaxy just at the price of one machine because of the self-replication capability. It goes to the next star system and then builds copies of itself. And then within a very short space of time, I think the number was 10 million years or so, you will have completely permeated the entire galaxy. If these machines existed, they should be in our solar system now, or there should be evidence of them, and there is none. So the argument goes that because of the power of this self-replication technology, there are obviously no self-replicating probes in the galaxy, ergo, there is no extraterrestrial intelligence. And that's essentially the argument.
In a matter of speaking, when you got into self-replication, there were already pre-existing or decades of pre-existing definitions of self-replication and what that meant. And, there's a huge chunk of history that was behind those two words and what they meant. When you came in and when you started to look into this a little bit further, how did you start to define self-replication? Like, what did it mean to you? And what were the things that were required in order for you to define that as self-replication? Like, what were some of those variables?
Sure. Yes, there has been this long history about differentiating between self-replicating systems or self-reproducing systems and so on. To be honest, I find them to be a bit moot. I tend to use the two terms synonymously. There are two schools of thought about self-replicating systems. One is that you could create this system which can produce copies of itself. It's generally fairly simple, and almost trivial in a sense. But as an engineer, this is not very pragmatic. It's not a very practical machine, because all it does is just consume resources to build more copies of itself. It doesn't do anything useful. To me, a self-replicating system basically harks back to von Neumann's original concept. And in that concept, when he looked at self-replication, he understood it as the main property of it was as a universal constructing system, a universal construction system. So what this meant is that a universal constructor is a machine that can build anything it's programmed to, given the appropriate resources, energy, information, materials, given the kind of like the appropriate programming, and can build anything within reason, including a copy of itself. So the self-replication is like a side effect of the universal construction mechanism. And to me, this is where the value of the self-replicating machine comes in, is because it's not just a self-replicator, it's a universal constructor. So the self-replicator can be reprogrammed to build anything you want. And that's where its value is. It's not just it's a general productive capability. So when you build a self-replicator, it then self-replicates. What you're doing is you're exponentially growing your productive capacity. And that's really where the value lies.
Okay, so you've shifted in a sense from looking into I guess you could say, abstract concepts of self replication towards the actual practical applications on the moon, right? So, what would be those basic elements or components that are needed to create self replicating systems?
Okay, that's kind of a big question. Okay, you can imagine it like essentially, assuming humans are not in the loop, and this is an assumption that I make. A self-replicating machine is a robot, and it has all the components of a robot. So you have in a robot, you need structure of various kinds to keep the thing together. You need electronics to control it. That includes computational electronics. And you need actuators, motors, and that allow it to move around in its environment. So you can see how each of those components, what a robot is like it's a mechanical organism. So the self-replicating machine taken in toto is a kind of organism, a mechanical organism. So far, we've been focusing on looking at electric motors as one of the key components of a self-replicator. We're also looking at electronics, we're looking at sensors and so on and so forth. So all these pieces are essential. We have to be able to manufacture all these bits from local resources. We also have to provide energy as well to support this system. And of course, we need information for the programming. So it's an entire system that involves everything that you can imagine that you'd need in any kind of infrastructure.
So, you mentioned before that you've been interested in self replication for decades, but only recently you've been working on a solution for creating self replication in space, right? So, why? Why now?
Because of the confluence of several different things. One was, the freedom to work on this once I was promoted to full professor. But it also coincided with two main things. One was that I started getting involved in in-situ resource utilization. But I was interested in in-situ resource utilization in pushing the boundaries as to what we could actually extract from the moon and what we can use from the moon. The other issue was that was the advent of the RepRap 3D printer came on the market. And that was quite an inspiration, really, because it was actually made by somebody I knew called Adrian Bowyer. And it was basically a 3D printer with plastic components which were made by its parent. And it could manufacture parts of itself. some parts of its plastic components. What was inspirational about this is that when I bought one, I was looking at it and I was thinking, well, what do we need to complete that process of self-replication? There are electric motors that need to be 3D printed and the electronics boards. And so I started focusing on those two things and sensors, of course. And of course, a 3D printer is simply a Cartesian robot. So again, it is a robot system. So,
you personally have called for the lunar industrial ecology. Explain to us a little bit about what that means and how you see it playing out over the next decade, or even more over the next 2 decades, as this Artemis program or other sort of relevant programs, the global exploration roadmap, and who would be the key parties here?
right. Okay. The difference between what I've been doing and what most people are doing through Artemis and so on, most people have approached it from the idea of going to the moon and saying, okay, what can we do to create some kind of economy on the moon, some kind of marketing economy of some kind. And so everybody's focused on water. And water, of course, if you can get that from the poles, which actually is going to be harder to do than I think most people imagine, you split the water into hydrogen and oxygen, you have basically LOX LH2 propellant. And the idea behind that is that you can mine this, you can then sell it to, let's say, maybe NASA. NASA wants to put people onto Mars, so you basically gather all this LH2 LOX and you launch it to the gateway and store it there, and then to fuel a Mars mission. So if you crunch the numbers, yes, that is feasible. So I can't remember the numbers exactly off the top of my head, but it's I think it's something like 600 tons of LOX LH2 that you need to get to Mars and back. Now, obviously, if you supply that from the moon, that's stuff you don't need to bring from Earth and launch from Earth, but you still have to launch it from the moon. Now, you could use LOX LH2 to launch that from the moon. You'd need about 2.5 times more LOX LH2 to launch that to the gateway. So you're starting to increase the tonnage that you need to consume. The other alternative, which I think would be a better approach, would be to use something like electromagnetic launchers to launch that LOX LH2 to the gateway. And you'd save 3/4 of the amount of LOX LH2 that you mine. So most people are focused on this water. Most people are actually looking at using regolith and mixing binder to create the outer shells of bases. What I've done is, because I was looking at self-replication, I've looked at it from the other way around. Rather than actually trying to figure out, what to use, what I've been trying to do is figure out what we can use and maximize our utility of what's available on the moon to do useful things. So I start out looking at how would you build a spacecraft with all its thermal requirements and its electrical requirements, its structural and so on and so forth, and what materials are available on the moon that we can actually use to implement those functions. So things like structure and electrical wiring and all this sort of stuff. So I was looking at it from the point of view, I want to create a self-replicating machine on the moon, which requires all these capabilities. How can I get that out of the moon? So what I was taking almost like an indigenous view of going to the moon, living off the moon, building a technology on the moon from the moon, rather than actually transporting a terrestrial technology with a vast infrastructure behind it and then putting that on the moon. So it's trying to create a selenite technology, if you want to call it that. So I was looking at the industrial ecology, came about by looking at the minerals that we have on the moon and how we extract useful materials from those minerals and how we can do that most efficiently. So it's basically trying to use as few processes as possible, minimize the amount of energy we need to use, and minimize waste. The output from one process feeds into another. And so we recycle everything. We waste literally nothing. Well, I say we waste literally nothing. We have product, and we also have things like salts and clays as waste product, essentially. Industrial ecology was built for the self-replicator to minimize the amount of energy we need to use because of the closure constraints that we have with the self-replicator. And this turns out to be quite useful for the moon anyway, because it means we're essentially, by adopting this ecology, we're actually providing a sustainable approach for a lunar infrastructure. So, and that essentially is a side effect, a side product of this self-replicator. So I've come at it from a different viewpoint, a different direction to most people's approach to the moon.
So, in terms of sustainability and looking at it from that perspective, who would this benefit from a sustainability perspective? And that idea of lunar industrial ecology, why create it in the first place? We went through the stage of industrialization in history, and because of that, we are now suffering the consequences of that industrialization age. So, how can we make that different when we go to the moon with this self-replication aspect?
Sure, that's a really great question, and actually there is a problem, and that is that the concept of sustainability is understood by everybody except space engineers, who use the term sustainability as a short form for affordability. Now, sustainability means that we don't destroy the environment so that it degrades future generations. That is how I use the term sustainability. Now, the way space engineers are using the term sustainability is what they mean is they minimize the amount of stuff so they don't have to supply that from Earth because of cost. It's an affordability issue. The two are connected. But the problem is that what NASA wants to do is they want to take that very scarce and valuable water and they want to burn it as propellant. Now, once that's burned, it can't be recycled. It's basically lost, essentially, which is one of the reasons why I've been suggesting that maybe we should have electromagnetic launches on the surface of the moon to launch this stuff to the gateway to save some of that water. Now, where sustainability comes in, if we can imagine ourselves in the future going even beyond a lunar village, a moon village, to, let's say we have to start building towns and things like that where people live and work on the moon, they are going to need water. And if we burned it all, then they're not going to have that resource. We need water for not just for drinking. We can recycle a lot of that. We need it to support industrial processes. We need it as coolant. We need it as like partial lubrication with oils and things like that, in all these industrial processes. And that's going to be more difficult to recycle. In any kind of recycling system, there's always going to be leakage. So what I think we should be doing with the water, we should be husbanding it. We should be taking care of it. We should be utilizing it, storing it for future generations because they're going to need it for other processes. And if we're burning it, that is I think that's a terrible thing to do. And I think we're bringing all our bad habits with us by doing this.
Okay, so you are a proponent of developing self-replicating machines, right? As a critical kind of practice for creating a sustainable ecosystem on the moon, right? Whereby you have resources that are recycled or waste that is either reused or at least minimized, right? And all this is done within a closed system, which in this case is the moon, right? So now we have all these necessary components that you mentioned: materials, programming, energy. Now what? Now all these components, how do they work together to make an actual self-replicating machine?
Sure. That's actually something we haven't done yet, is how do we put it all together? I mean, what I've been focusing on is building, if you can imagine the origin of life. So the origin of life it wouldn't have started from an architecture. It would have started from the ground upwards. So the components had to be built first before they could come together to create a cell or whatever. And this is the approach I'm using, is we're trying to create the components first. And then once we got that working, then we will start to look at the overall architecture. At the moment, I haven't got an architecture apart from inside my brain. I do actually have a picture which I could probably send you, an artist's representation of a lunar self-replicator, which I had commissioned actually only a few weeks ago. So yeah, in terms of like putting it together, my preferred approach would be to, what I would like to do and try and convince CSA that we should be doing, is to build a tech demo. Now, the tech demo would scoop up regolith, put it into this black box, and out of the black box pops a 3D printed article. Within that process, we'd do things like grinding, and we'd basically do the HCl treatment to extract the alumina and silica. And then we'd cook that in an electrolytic cell to produce essentially aluminium powder, which would then 3D print into an article. That would show at least the core of not just a self-replicating system, but any kind of manufacturing system you could adopt on the moon. That's what I would like to do, is demonstrate that we can do that on the moon on a payload, and then look at the architectural issues maybe a little bit later. But I'm pretty certain that once we got the basic components there, and we can demonstrate the basic components, then the self-replicator system would fall into place, as long as we observe the constraints of closure, by minimizing the amount of materials, minimizing the number of parts, minimizing the energy, adopting sort of like computational architectures which can be supported by the moon. And obviously sensors. I wrote a paper on sensors, for example, IAC, which was looking at some of the problems you might encounter.
Yeah. And we'll come back to that. We'll definitely ask you about that, because I'm very curious about what you ended up presenting and how that was received, because you're in a position where not a lot of people are working on this topic per se. So I just had one point of clarification. As you mentioned, you were talking about energy. And when you talk about minimizing the energy, is it both your input and the waste heat output, the thermodynamic cost, or are you just optimizing the input?
Basically, the higher the temperature you require, the more material you need to generate it. So let's say you're using Fresnel lenses. If you have a Fresnel lens, it basically creates a hotspot, which you can then heat to provide thermal energy. The higher the temperature you require, the bigger your Fresnel lens needs to be. That in turn imposes a requirement for your throughput for your self-replicator. So you want to try and minimize the size of everything, to minimize the footprint that you need to manufacture to generate energy. In the conversion process as well, if you're converting from light or heat energy, you want to maximize the conversion efficiency. So again, this reduces your footprint, because the bigger your footprint, the more you have to manufacture for your self-replicator. You want to try and keep it as compact as possible.
Okay. Just out of curiosity, is there an upper limit to what that compatibility could align itself to? Because we're on the moon, the atmosphere is potentially thin. So I guess I'm just curious about that.
The atmosphere is not really, actually the lack of an atmosphere is potentially an advantage, because the Earth's atmosphere is oxidizing. It tends to create problems for metals. And in fact, aluminium not so much, but certainly iron it tends to be sensitive to oxygen. People very rarely on Earth use wrought iron. You tend to use mostly cast iron, because it basically makes it less susceptible to rust. Whereas on the moon, we can use wrought iron, we can use pure iron, because there's no atmosphere there. In terms of looking at particular materials, anorthite is a common mineral on the moon. It's in the highlands. We've been doing experiments on this actually. You can basically treat it with HCl through two processes. The first process, you deposit silica, and in the second process, you deposit alumina, and the leftover is calcium chloride. Calcium chloride is part of the electrolyte required for the FFC process. And the silica itself and the alumina are both highly useful materials. So silica you can use as glass to create fused silicon glass. You can use it to create fibers. You can use it to create glass cloth as an insulator, thermal and electrical insulator. Alumina itself is very, very hard. It's second only to diamond in terms of its hard properties. You can use it for crucibles, high temperature crucibles. You could also reduce it into aluminium. Aluminium is extremely useful. It can be used for tensile structures. It can be used for electrical wiring. It can be used for thermal radiators. It can be used for thermal straps, thermal conductors, and so on. So what I'm trying to do is use the minimum number of materials, to maximize its use. So we want to get materials which we can use for multiple things. And even on a parts level, we also want to do that. So I was talking about, I think a little bit earlier, about electric motors and electronics. Now, one of the things we can do with electric motors, we would traditionally use that for actuation and for moving around and acting on the environment, but you can also use it for energy storage in flywheels. So essentially what we're doing, we're learning from nature, where nature quite often coexapts one particular function for another. So feathers, for example, bird feathers originally evolved for thermal insulation, then they were adapted for flying. So we're doing essentially the same thing. We're using the electric motor, which we originally used for actuation, but we can use that for energy storage. And similarly with the electronic, instead of using solid state electronics, we can go back to vacuum tube based electronics. And this is what we've been looking at. Again, trying to minimize the number of components we need and utilizing components in many different ways. So, and again, this points towards the closure problem of trying to close the self-replication cycle.
Yeah, so I'm also curious. You have some other very interesting applications for developing an industrial lunar ecology that you discuss in some of your research papers, right?
I'm glad somebody reads them.
At least the introductions and conclusions.
Yeah.
No, but in one of your papers, you talk about solar powered satellites, right, to combat climate change. But as far as I understand it, rather than manufacturing those solar powered satellites on Earth, you're saying we could do so on the moon. How does that work?
Yeah, I think again, a lot of it boils down to the problems that NASA have is in trying to create a market. The market in space is always going to be small and not much of a driver. The only way you can create a market is to bring it back to people on Earth. And of course, there's also the issue about space exploration. Is that relevant? Is it necessary? My argument would say yes, it is. But there's a practical reason for that. And that is, if you look at the moment, we're all aware of the environmental issues, global warming, and so on and so forth, and how we're not tackling it particularly well. One approach which could be potentially useful for providing clean energy to the Earth is the solar power satellite. Now, this has been around since the late 60s. This concept is to create these giant sort of like solar arrays, which are then convert to capture solar energy, convert them into microwave using magnetrons of various kinds, and then beaming that to Earth. A relatively low density, but much higher density than you get from, let's say, from solar on Earth or wind. So if you crunch the numbers, the solar power satellite concept can yield about 230 watts per square meter in terms of energy. If you compare that to wind, it's about 100 times greater than you get from wind, and about maybe 10 or 15 times greater than you get from solar energy on Earth, because it's available 24/7. It doesn't suffer from the nighttime issue. And it means that in theory, we don't need any energy storage devices on Earth. But of course, the big question mark, the thing that everything hangs on is the cost of launching all this stuff into space is prohibitive. It would cost more than the world's GDP to do this, if we were to do this globally. If we want to supply, say, 20 terawatts of energy, which is our current energy consumption, you would need to put a ring around geostationary orbit about 1 kilometer wide. And the cost of doing that would just be so huge. So this is where we look to the moon. If we could build solar power satellites from lunar resources, then we don't have to launch them there. They're already on the moon, which actually has a much lower gravity field than the Earth. And this essentially lowers the cost. And again, this is an old idea. Gerard O'Neill suggested this in the 1970s. So this is none of these ideas are really new. O'Neill originally suggested that you have these giant orbital cities in orbit around the Earth, constructed from lunar resources to house people. What I think we should be doing is, again, the concept is sound, going to the moon. How can we actually leverage what we need from the moon to build solar power satellites? But we need the infrastructure there to do it. And this is where the self-replicator comes in. So the idea is we build one 10, 15-ton device, self-replicating machine. It then produces copies of itself, grows its productive capacity exponentially. In just 13 generations, you have 1.5 million units. So if each generation takes 6 months to build, then you have 1.5 million units in 6.5 years. So that's a phenomenal industrial capacity you could build using a self-replicating machine. And then once you've got your capacity, you can then program them to build solar power satellites to launch around the Earth. And that makes the idea of a global system realizable. And it's only realizable because we have the self-replication capability to grow that capacity. First of all, I think this is the only way we're going to solve many of our energy problems in a robust way, and also make it relevant to everybody on Earth. So space exploration does do something for people on Earth. And the second aspect is I think this is the key to colonizing our entire solar system and eventually the stars beyond.
You know, I'm glad that I found that I keep finding people who are on the same page as me, because I've been saying that about NASA, that NASA has this sort of ultimate problem where it's trying to build a market where the market not necessarily isn't present. And sometimes it's forcing it, which often turns into, an entirely different piece of the conversation. But I want to ask you about timelines, but I'm going to wait on that because I have a better question. How does self-replication help save water on the moon? I mean, should people just leave water on the moon and not exhaust it in space? Like, is that what should be done with the water that is processed?
No, I'm not. I'm not implying like oil. We should leave it on the ground. What I'm saying is that we should use it carefully. So we utilize it, we recycle it. So basically, whatever for example, for human support, we could recycle urine and so on and so forth. If you want to do, sort of like agriculture on the moon, most likely way would probably be hydroponics. So we need water as the conveyor of the nutrient to the plants, but you can recycle that, it's like with greater or lesser efficiency. But burning it is not recycling it. It's burning it is just not. It's not. That's just getting rid of it entirely. There's no way to recycle that. We'll also need it for industrial processes. So again, we can recycle that if we design things carefully.
Excellent. Hey, thanks for that. I think that kind of clarifies the point a little bit further. Now, coming back to the question at hand, we want to talk a little bit about timelines, regarding where we are with the development of the technology and the projected plans for the moon and the number of missions that have been planned, along with, going beyond the moon. Don't forget that, because that's our sole purpose of getting to the moon, as far as I know. How soon is all of this going to happen, in your opinion? Or how soon should it happen? And how soon will it happen?
At the moment, the how soon will it happen is never, because there's no funding for this. I do pretty much everything I do on a shoestring budget. The Canadian Space Agency thinks I'm mad as a hatter. There are groups around who have an interest in this, but again, living in Canada, I can't access American funding, of course. Europe is actually probably a little bit further down the line. They I know are actively promoting one of the processes that I built my self-replicating architecture around. That's the FFC process, the electrolytic salt electrolytic process. I think again the emphasis. It's interesting that most people are focused on consumables. Water, generating oxygen by basically reducing metals. That's great, but they're not focused on the metal part, which I am, and the ceramics part, which I am. I think we could, with very little effort, bring the two approaches together. The kind of like the agency's approach and what I'm proposing to do, to make it a bit more kind of coherent. But the self-replicating machine approach is high risk at the moment because it's not technologically mature. In terms of like how long would it take us to get self-replication up and running? Well, I think given the appropriate funding, I see no reason why it can't be done within 10 years. I mean, we know what to do. We know how to do it. It's a question of actually putting it together, and all the pieces, most of the pieces are already there. It's just a question of putting them together. I think it could be done within 10 years. And of course, once that happens, then everything changes, because you launch your self-replicator to the moon. You don't have to do anything else, because if you improve it, you send up a new program to improve it. So you don't actually physically have to send up anything else after that, because you can reprogram it to build something else. So in a way, a self-replicating machine cannot become obsolete. So you can always update it and upgrade it, remotely. I think the power of this technology is immense. The problem then becomes, well, how do you make money out of it? Well, I personally think it's too powerful for anybody to should be making money out of it. I think everything we do is open source. We publish everything. I think it's too powerful technology for anybody to own. And of course, that then brings the problem, well, how do you get private investment? No private investor is going to invest in it unless they can make money out of it. So it's a bit of a chicken and the egg. I think that this sort of thing should be funded by governments because I think it is an investment. Imagine the power of self-replication technology on Earth. So let's say you put self-replicator into the Sahara Desert and it self-replicates itself into the giant carbon-sucking machines to try and suck out carbon out of the Earth's atmosphere. It makes these things possible. Imagine, for example, you can have a self-replicator which you can fit in your garage. So you could basically put one in Africa, and within 10 years, every family would have a self-replicator, and they can generate their own energy. So because the self-replicator has to create its own energy from solar. So it provides an industrial, it's almost like an industrial revolution, but not collective. It's a personal industrial revolution. So everybody can build whatever they want for themselves with a self-replicator, assuming, of course, they have the kind of material resources. But again, one of the advantages about going to the moon is that we're trying to extract useful materials from common rock-forming minerals. There are no ores on the moon in the same way that there are on Earth. So potentially we could use common rock-forming minerals to extract useful materials on Earth. So it would get away with this distortion between ore, where ores reside on Earth, in Congo or wherever. But it smooths over those distortions by allowing us to utilize common rock-forming minerals. It's a step in that direction anyway. So
Wow. So that really opens up a whole Pandora's box of more questions I have, I guess, around ethics. But well, let's talk about sci-fi doomsday scenarios, right? Regarding self-replication, where you have a self-replicating robot. Whether you're in Africa or on the moon or elsewhere, and it won't shut down or it's gone out of control. What then? How should we start thinking about fixing that self-replication gone rogue?
sure. That's a great question. This is actually the commonest question I get from people in the general public is, what about these things going crazy out of control, the grey goose scenario and that sort of thing. So, and the answer to that is really in three parts. The first part is that trying to get the self-replicator to work is a devilish job in itself, just trying to get it to work. There's a high barrier to try and get it to function correctly and work properly. And the second one is that on the moon actually is relatively straightforward because built into our lunar industrial ecology is that we need to import salt from the Earth or from asteroids. Now, the thing is that salt is not actually consumed in any product, but it is a reagent which is recycled through the industrial ecology. So essentially, if you're trying to build a self-replicator, every generation is going to require more salt. So by supplying salt from the earth, we effectively invoked a salt contingency. We can deny it salt, so it can't continue to replicate. We can also do the same on the moon. Now, things like what I call tunicose elements, tungsten, nickel, cobalt, selenium, will be located actually mostly in nickel ion asteroid material. Now, there are only certain locations on the moon where we think they are. One of them is near one of the South Pole craters. And so by centralizing that particular facility, acting as a supply to the self-replicators, we actually impose a moon-based tunicose contingency. So we could deny those types of materials. So we essentially have two kill switches built in. Second approach is to ensure that we do not, in the programming, we need to ensure that if we impose things like limits in the number of self-replication cycles we can do, telomeres, telomeres in cells act as a counter to number of replication cycles that the cell can do. We can implement the same thing in a self-replicator. So once it's replicated a certain number of times, it then can no longer replicate itself. And we can implement this in a genetic way. And then the final approach is which is particularly of concern to an interstellar spacecraft, is to implement error detection correction codes so that any errors get corrected, within the life cycle, the population cycle of the self-replicator. So there are several approaches at which we can employ, and I've been looking at one of them. I'm currently looking at the error detection correction coding at the moment. And so, these are all approaches that we can build in these safeguards to prevent uncontrolled replication.
Oh, just to follow up, I think the examples you gave are related to a mechanical or machine-based system, right? What about when we apply that concept to biological self-replication or even synthetic biology?
Well, biological self-replication is usually limited by resources. So, for example, with disease, we've all experienced COVID. We know that as long as people are walking around, it's like infecting each other, that virus can continue to mutate. If you stop it from spreading, it doesn't have the opportunity to mutate anymore. And so it then can be essentially killed, essentially. One of the things I'm looking at actually at the moment is trying to figure out how biology implements error detection correction codes. And biology takes a very different approach to the way we would take things as an engineer. So, for example, when you look at DNA, when it divides, there are various kind of proteins that unzip it and read it and so on and so forth. And you've also got error correcting proteins, which change out bases and things like that. It is all based on the distortion in the DNA shape of the molecules. That is not the approach we would use in engineering, because the difference between a flip-flop that stores a 1 or a 0, it doesn't change its dimensions, where it's got a 1 or a 0 installed in it. So we have to do it logically. So we have to do things a little bit differently compared to biology. There are some similarities, some things we can learn, but they are two different approaches. One can swing this around the other way and say, well, if we build a self-replicating machine, is it alive? Because it has all the major properties of life. If we look at the Joycean definition of life, we have genetic material, we have some kind of information storage, some kind of metabolism, self-replication, and evolutionary ability. All of those potentially could happen in a self-replicating machine. The only difference is that instead of its metabolism is based on high heat instead of enzymes. Enzymes are catalysts. Is there any difference in principle between having something cooking metal as part of its metabolism as opposed to some kind of enzymatic reactions using carbon, nitrogen, oxygen, phosphorus, and sulfur? I think it's an interesting question. I don't know the answer to that. Would it be creating a life form? I hesitate to think that it is, because as an engineer, I feel that it's not alive. And so I can't exactly put that into any reason why I think that. So I think potentially it's an open question.
Yeah, we're getting into the realm of metaphysics or maybe alchemy, right?
Yes.
Well, let me ask you this. I think we've talked about quite a lot of stuff in terms of where self-replication is and how your sort of research has focused on very, very niche concepts and very unique elements of what to do in response to lunar ecology, right? Industrial ecology. So what do you see as the next step for self-replication beyond the moon?
Beyond the moon?
Beyond the moon.
Oh,
We haven't got to the moon yet, but
yeah.
I think we're already thinking beyond the moon. So I think we're in the same alley that you're in, but for the moon.
Sure. Yeah. Obviously, I think once we developed for the moon, I think it basically would be very quickly adopted for, essentially, you could send it to Mars. I mean, one of the things about Elon Musk's ideas a few years ago, when he said he wants to take 1,000 people to Mars in one of his big rockets. And that's great. But once they're there, they're all going to die because there's no infrastructure there. The self-replicating machine could develop that infrastructure and develop it very quickly. And again, you could send this machine to Mars to build, whatever you need to build, an industrial capacity on Mars before the 1,000 colonists get there. We can go beyond this. We can mine things like the outer solar system moons, the asteroid belt. The asteroid belt in particular, and near Earth asteroids potentially could. I was looking at that actually a while back, looking at mining asteroids. Many of the same materials you get on the moon. Actually, asteroids are even richer than the moon. It's in terms of like its resources. The self-replicator would enable us to basically colonize our entire solar system very, very quickly, very rapidly, and also out into interstellar space as well. People are thinking about interstellar flight at the moment. The Breakthrough program is looking at interstellar exploration. There's no reason why, if we could develop some of the propulsion technologies, solar sails, and so on, then there's no reason why we couldn't start sending out what people call von Neumann probes fairly soon, within 50 years.
Oh, maybe one more thing. I'm just curious. Earlier, you were talking about how you shifted from astrophysics to robotics, mostly because you became a skeptic about ETIs after reading Tipler and Barrow's book, right? And you specifically used the word hope. You said that you hope there are no ETIs. Why did you say that?
Well, if you most of the ETI proponents basically exploit what is known as the Copernican principle. So the Copernican principle is that given no other evidence, we tend to assume that ETI are going to be like us. And the reason why I say I hope not is because we're not exactly angelic in our natures. We can be pretty brutal and pretty horrible as a species. And of course, one might expect other ETI to be similar, or might be similar. There's always been an assumption that as you progress, as you advance, you become more benign. I'm not necessarily convinced that's true. And so from that perspective, the history of our own planet shows that when one advanced race comes across another, they tend to subsume the less advanced race. Of course, if we universalize that, that potentially could be an issue. Going back to Tipler's argument, I do think actually that we are probably the first ones. The evidence suggests that we are the first. There's no evidence of any other intelligent species out there. So I think we should be going out there to explore. I hope we would do it in a responsible way.
So, Alex, one of the things that keeps coming up in this discussion about self-replication is that whether or not a self-replicating machine is a version of a copy or a copy of itself, or it's this idea of growing up from a seed, like an apple tree of sorts. What do you think? How would you define that?
I mean, what you can imagine is that, okay, you're sending this seed system to a stellar system, another stellar system, and then it has to build up its capacity until it's reached full capacity or adulthood, if you want to put it that way, and then makes copies of itself. All this is doing is, at least in my mind as an engineer, is you're creating like a subset of the basic functionality, which then has to grow. When you say growing, I think of it in terms of building the additional capacity rather than a learning process. Now, going back to learning, this is an interesting point because one of the things that we've been doing actually, we've been creating neural net circuitry as our computational unit, as it were. And one of the things we've done more recently, we've also built back propagation algorithm in circuitry as well. Now, what this introduces is the possibility of learning. Now, once you allow learning, you then lose control, because learning obviously means it's changing its program, essentially. However, having said that, you can control that learning process by having a predefined architecture. So it's limited to that architecture. So it can't learn outside those boundaries. So one of the things we haven't implemented, for example, is growing neural networks and, sort of like neural networks that delete links and things like that. Although we could implement the deleting links, the growing architecture would be very, very difficult to implement physically because you'd have to print that. So, yes, there is this issue of controllability, and this goes back to the idea of using error detection correction coding to prevent any changes in the program to ensure that it remains stable over evolutionary periods. And even if you look at the entire galaxy, if you want to colonize the entire galaxy using self-replicating machines, you can do it in 26 generations. So that's not that many generations of which to control your error growth. So that potentially could be achievable.
Well, Alex, I think this is, we always ask this one question before wrap up, but I just want to say that this has been a very fruitful conversation, I think, to all of us. And
pleasure.
Myself and Matthias, very especially, because we've been very interested in this topic, and to talk about it with you, it's been really a pleasure. So thanks for taking the time.
It's been a delight. Thank you.
But our last question, why do you think that us as a humanity should move space forward? So why do you believe that space should continue to move forward or will help humanity in moving forward?
That's a great question. I do believe that we could talk about things like, it's like exploring, it's in our nature and so on and so forth. I actually disagree with that. I think what has motivated most of humanity in terms of exploration has been greed or power. That, in a way, is a sad indictment of the human species, but I think that that's the reality. So from this point of view, I think space exploration will only survive as a mainstream activity as opposed to a peripheral activity that it is now. It will only survive when we can make it relevant to every man, woman, and child on Earth. And I think that solar power satellites is that mechanism, because we can provide clean energy to Earth. In a way, it's like saying, as a species, we've already outgrown planet's capacity to support us. So we have to go outside to bring that energy in more efficiently than it does at the moment. So we need to give nature a bit of a helping hand. To me, that's the key to our survival. Once we have developed that infrastructure to do that, self-replicating machines in particular make everything else low cost, low capital cost. We'll simply go out to asteroids and so on and so forth, because the cost of doing so will be a very low barrier once we've developed self-replication technology. Does that answer your question?
It definitely answers my question, and I'm sure that is a unique perspective, and I think it's very, very valued. So thank you so much for taking the time. We really appreciate it. Not appreciate it.
It's been fun.
Yeah. Thanks, Alex.
Sure. It's been an absolute pleasure. Thank you very much.
If you're still listening, a word from your sponsors, which
is essentially us. Our team works really hard
to bring you these enlightening conversations about
the future of space exploration.
And yes, you are vital for fueling our podcast and making sure that we don't disintegrate into the vacuum of outer space.
So if you like Space Forward, give us a thumbs up. And if you love Space Forward,
well, then share that love and recommend this podcast to a friend. Meanwhile, stay tuned for episode 16 with Jason Wright, a professor of astronomy and astrophysics at Penn State, as well as its director of the Extraterrestrial Intelligence Center.
We'll get into the nitty-gritty of searching for techno-signatures.
Thanks for listening, and peace out.
Why do we say peace out? What is this, the 70s?
Okay, take two. I'm getting all your little ha-ha-has in here.